We looked at in the earlier section transition in freezing. So, we started with the gas phase, we lowered the temperature, we watched atoms going into a droplet, which is forming some liquid, and then you could see that inside the droplet there are also some clustering of the atoms into a crystalline phase. At the end of it, we ended up with the two blobs, which were essentially condensates. So, that was a situation where we traversed in EVN ensemble. We looked at that and we were making sure that we are able to see that transition with the temperature changing. So, now we are starting with the reverse of that, and this reversal is going from a, let us say, 1000 particle. Again, we will start with the crystalline phase and see how it melts. So, here is the block that we are starting with, and this is essentially a solid block of, let us say, argon, and this is a very simple calculation with, let us say, Leonard-Jonesian potential function, and 1000 particles, volume is fixed, E V n. So, V is fixed, n is fixed, and we are essentially also keeping the total energy or the energy terms constant. Now, we are going to move into temperature and time profile, and then we will look at potential energy versus time profile, because potential energy we are going to look at the transition. So, that when we start with a particular value, so let us look at some of the average values. So, we are starting with the potential energy minus 5631, and that is in joules. So, we are looking at that. Time elapsed 3500, pressure is 5.7 e to the power minus 6, very low pressure right now in the system, and total energy is very low. So, this we are looking at that. Now, let us go, let the system move. We stop here. Now, you can see at the internal region, you can see still there is a structure which is indicative of the crystalline model. And so, now let us look at some of the properties, but outer layer is also becoming liquid like. You can see the droplet model here, where at the center there is still the core which is solid, but outside is starting to melt, and you can also see some gas particles out there. And let us look at some properties now one more time. So, if you look at here, we are looking at potential energy minus 5095.738. Now, pressure has gone up 1.04 e to the power minus 4. Temperature is also gone up from 0.1 to 0.4 in reduced temperature units. So, now let us look at how it goes forward. More and more part of the crystal is becoming liquid, and as it is becoming liquid, you will see also changes in the vapor part. Move forward. Now, I will let the system go again, and these are the time units that you are looking at the bottom. Let us stop it. Now, you can see this is almost liquid like, and this is a phase which is sometimes also called amorphous if there is a transition taking too fast with the temperature going down. And if you look at, this is the location of the atoms, we have put atoms around it with the radii that we are defining for that. Now, if you look at, this is average movie. Now, we will move forward and see how we can reach the gas phase, but before that I also want to look at some graphs, this temperature versus time. Now, we are looking at potential energy changes, and if you look at these pressure versus time, you are also looking at that. We'll move forward. Now, you will see the melting transition for this ensemble, and you can see the pressure is continuously growing. Let's look at the temperature. We are essentially connecting it to the temperature bath, which is continuously increasing temperature. And then if you look at the potential energy, there is a sudden increase in the potential energy, which is indicative of the phase transition. So, this is where you can see, and again this is great thing to learn about new phenomena, because I can go backwards and go all the way back into my movie and move forward and backward both ways. So, as you can see now, from the gas phase, I am going back to the solid phase by freezing. I can stop and I can go forward, and so this is the trajectory which is calculated. And now with these ideas, you can observe the changes in potential energy parameter, at what point the potential energy is changing. So, let us stop it here, and then we go back and now only observe the potential energy changes throughout the movie and see what has happened to the value. So, we are now reducing in the, it is all in minus. So, it is going down. You can see the changes happening. Now, if you look at the order of magnitude wise, there was a sudden change in between. Stop here, I will go back again. I am heating the substance again. So, this, if you look at minus 2.42 was the value here, and you will see at certain point there is a change in the potential value. So, this is the gas phase, and so it has gone very, very low. So, let us start with minus 1.42. So, you watch the slope of this curve. So, this is still going in the linear direction, and the slope is increasing, and as it becomes solid, the slope becomes quite steep. So, if you look at in this case, now you have seen the melting transition going all the way back into the solid phase. So, if you plot a curve between temperature and potential energy, what you will see that there will be certain parts between the liquid, solid and gaseous phase, they are disjointed, and there is a jump, and those jumps are indicative of the changes in potential and potential energy leading to the phase transition. So, these two phenomena, melting as well as freezing transitions, shows you that on a given ensemble situation you can observe that. But let us say if I wanted to see the transition due to pressure, this will not be the ensemble I can use. I have to use isothermal and isobaric ensemble. So, again, what is the question? This is where we go back to saying that is one ensemble better than the other? It depends on what question you are asking. If you are talking about pressure induced transition, then you have to use isobaric isothermal ensemble. If you are looking at the energy transition due to temperature, you can use EVN and isochoric transition, both can be applied. So, again, depending on the question, you will select an ensemble, and then you will also simulate those conditions in the boundary of the box. So, if you had a isobaric situation, then your box has to adjust with the pressure, because you have to make sure pressure is constant. So, you cannot have a fixed volume system and create an isobaric model. So, what you have to do is a moving piston model or boundary where the box can adjust its volume based on the pressure which is created inside the system due to the kinetic theory of gases. As you increase the temperature, then the volume should expand and keep the pressure constant. And this is where we can look at the stress strain curve under different kinds of pressure which is being put in. So, that is the stress we are giving, and how the system is changing its volume, which is the strain curve. And with that, if you want to calculate for a, let us say, metal, you want to calculate all 6 or 9 different elastic constant, which is elastic constant in x direction, which is for a system which is anisotropic. That means, it is different in different direction. X direction has a different constant, y direction may have different elastic constant, z direction may be different elastic constant, and if we create that model, then we have to use a different ensemble. Let us say if there was a chemical reaction taking place, then obviously you have to use grand canonical ensemble. So, I think these are the situations you have to look at, think about the physical situation very carefully, understand what are the variables, what are the intensive variable, what are the extensive variable, and what is the situation, or what we also call is the thermodynamic potentials involved in that. So, if it is a melting transition and you want to look at the changes in the Gibbs free energy, and as you know, Gibbs free energy will there will be equilibrium of that. So, there will be transition from gas to solid or solid to gas, melting and freezing. If you draw that curve of Gibbs free energy, you will see at certain point they are all same, and that point is what we also call is the phase transition point. So, there are several ways to understand and pinpoint some of these transition and then compare that data with the experimental value. The reason you need to do that, because then you need to use the difference between a predicted value and the experimental value, and if they are not matching, then you have to adjust your potential function. So, now you go back to bonded and unbonded material and see which part we can adjust. What is the potential energy? Well, sigma, which is the distance which we are looking at between particles, and also we are looking at the potential energy, well, epsilon. We can adjust those parameters. Instead of repulsion part is 12, 1 to the r to the power 12, and the attractive part 1 over r to the power 6, we can change those. We can do 8, 4. So, maybe the repulsion is not as high. If we adjust those parameters, we can realistically then calculate the melting temperature or freezing temperature. Now, that is a very good point for you to make sure that you validate your theoretical computational model with the experiment, and that is extremely important for you to do successful molecular dynamics, that it has to have a very good match. If not number wise, that means exact melting temperature, but if the trend of melting transition is same, then also you can calculate. Thank you.